Want to discuss the Wiener-Ikehara Tauberian theorem. The proof I'm going to give is neither due to Wiener or Ikehara, but actually motivated or inspired by a 1981 article by D.J. Newman, in which he does a special case. Namely, he's interested most in the prime number theorem. But then I had my student Aksha to generalize the whole thing to arbitrary series, and she's written a paper on it, and I'm going to model my lecture on that. So last time we were looking at the the idea of we were looking at the Dirichlet series associated to a sequence. And we noticed that if you had the sequence, let's call it G of S for a moment, or maybe D of S for Dirichlet, then you can write this as an integral. Where A of X is the partial sums of A sub n. Now the interesting thing is, this came from Abel's lemma, right? Abel's summation idea. The idea is, if you knew something about the partial sums, then you can form this integral and obtain an analytic continuation sometimes when you had more information. Now the idea behind Tauberian theory is to go the other way around. Start from the integral and maybe deduce something about A of X itself. So before we had information on A of X led to analytic continuation of the Dirichlet series D of S. And now we want to go the other way. So to do that, let me begin with the following little lemma, which is of interest in its own right. Suppose that A sub n's are non-negative, and let capital A of X be some n less than x, A sub n. If the integral from 1 to infinity of A of X minus x over x squared dx converges, then A of X is actually asymptotic to x as x goes to infinity. This is an interesting lemma in its own right. So here you have a sequence of non-negative numbers, A sub n, and you form these partial sums, and if you have this integral which converges, then automatically you get an asymptotic formula. You actually get information on A of X itself. So let's try to prove that. Well, you say, suppose not. Then let's say lim sup, i.e. Lim sup. Well, let's say it like this. Then there exists lambda bigger than 1, so that A of X is bigger than or equal to lambda x for infinitely many x tending to infinity. Right? I mean, if it's false, of course, the other way around too, we have to take lambda less than 1 and go the other way too. So first I'm going to try and show that this can't happen for infinitely many x. And then we'll show a of x is less than lambda x, for lambda strictly less than 1 can also not happen by the same proof. So it suffices to kind of look at this thing. If that's the case, then notice that for such, let me put it this way. Let me say for a sequence of xi's that this happens. Fair enough? Then consider the integral xi to lambda xi, a of t minus t over t squared dt. Consider this integral. This integral, since a of x is a summatory function for non-negative numbers, it's an increasing function. So this integrand here, a of t, is at least a of xi. And by our assumption, a of xi is at least lambda I xi. And now change variables. Put t equal to xi times u. So that the integral here becomes from 1 to lambda xi minus u xi over u xi squared. dt is xi du. So the xi's neatly cancel. Okay, so you have now a number which doesn't depend on xi at all, and it's a positive number because lambda, the integral is going from u to lambda, 1 to lambda, and lambda is bigger than 1. Okay, so this is a positive number. Whatever it is, let's call it c of lambda. It's positive, right? But, so far I haven't used the hypothesis, which is this. The hypothesis says this integral converges. So if the integral converges, the tails go to 0. Therefore, this integral here can be written as the difference between two tails. Right? This integral here is the difference of these two integrals. These two integrals are tails of a convergent, right? Therefore, for xi sufficiently large, it's better be small, arbitrarily small, but it's not. It's bigger than c of lambda. So that's a contradiction, right? So this shows that lim sup of a of x over x is at least is at most 1. This shows lim sup a of x over x is at most 1. And similarly, you can do the other way around. I'll leave that as an exercise. Lim inf is bigger than or equal to 1, and therefore it's equal to 1. Okay, so similarly for the other. And then once you have lim inf equals lim sup equals 1, the limit is equal to 1, and that's it, you're done. So this idea course, this is not the way Newman says it. You can read his paper. This is not the way he says it. But I think this is more or less a neat presentation of the idea. So somehow getting convergence of this particular integral allows you to get this theorem about asymptotics. Okay. Now what we'll do, this is lemma 1, let's say. Lemma 2 is will look a little technical, but it's really not. So let f of t be a bounded locally integrable function and define the Laplace transform g of s integral 0 to infinity of f of t e to the minus st dt. Because f is bounded, a simple integral test shows that this converges for real part of s positive. So this is converges and defines an analytic function for real part of s positive. So the hypothesis, suppose g of s admits an analytic continuation to real part of s greater than or equal to 0. In other words, like I explained last time, there's an analytic function, call it g of s still, analytic in this region, but it agrees with this integral in this region. You can't use that integral in the region, in this region, because the integral is only that. But the conclusion of the theorem is then integral 0 to infinity f of t dt converges and equals g of 0. So this is where the complex analysis is going to come into the picture. So it's a remarkable statement because this integral a priori doesn't converge for real part s because it's 0, equal to 0. So all of a sudden you're saying it does at s equals 0 and it equals that value of that analytically continued function. So let's see how to. I'll come back to this proof of this thing. For the time being, let me try to apply this to prove the prime number theorem. Or to deduce the theorem that I just kind of rubbed off, more or less a of x is asymptotic to x. So let's try to prove, so we'll get to this proof in a second, theorem. Suppose a sub n's are non-negative. Let a of x be summation n less than x, a sub n. If the Dirichlet series let's give it a name, g of s converges absolutely for real part of S bigger than 1 and admits an analytic continuation for real part of S greater than or equal to 1 except for a simple pole at S equals 1. With residue 1, then A of x as x goes to infinity. So here's the remarkable property that if you have a sequence of numbers a sub n, and you concoct this Dirichlet series, which converges absolutely for real part s bigger than 1, and then this admits an analytic continuation. So there's where the complex analysis comes in. It admits an analytic continuation to this larger region, except perhaps for a simple pole at s equals 1 with residue 1, then automatically A of x is asymptotic to x. Okay, now how will I prove this? Well, the proof will rely on the lemma 1 that I wrote down first, which I rubbed off, lemma 2 here, okay? And so we have, on one hand, g of s is right. We have from the Abel partial summation trick that I talked about earlier. You can write your integral. You can write your Dirichlet series as an integral. Okay, now g of s minus s over s minus 1 I'm sure you can do the integration, okay? So you have dx over x to the s, right? You do the integration, you'll get this. So now, because I said that g of s admits an analytic continuation to this region, except for a simple pole at s equals 1, there it is. I've removed the pole, so this guy is now analytic. I mean, you should write s over s minus 1 probably as 1 plus s minus 1. Okay, so that you could see the residue is 1. Analytic for real part of s greater than or equal to 1. And now I'd like to apply that lemma, but that silly thing is saying real part s bigger than 0, so change variables. So change variables, put s into s plus 1. So g of s plus 1 minus s plus 1 over s equals s plus 1 integral 1 to infinity a of x minus x over x to the s dx. Okay? So if I divide out by s plus 1, I get something like this. And the left-hand side is analytic for real part of s bigger than or equal to 0 now. Okay, so this is the function, and I have to write this as a Laplace transform, right? So, huh? What? What, you're doing the integration? Okay, let's do it. X to the s, x to the minus s plus 1 over minus s plus 1, infinity to 1, that's equal to, well, that's 0 there, right? Minus, it looks like 1 over s minus 1, right? Is Is it s over s minus 1? Right? Is that your question? Is it okay? All right. So I just want to now write it as a kind of a Laplace transform. So change variables, put x equals e to the minus t. Or x equals e to the t, rather. Right? If you put change x equals e to the t, well, the x is going from 1 to infinity, so t is going from 0 to infinity. A of e to the u, e to the t rather, minus e to the t divided by e to the st, right? Dx is e to the t did I do this correctly? Yeah, it's t e to the t dt. So dx is equal to dt over e to the t. Okay. In other words, the this thing here is equal to 0 to infinity a of e to the t minus e to the t divided by e to the t times times e to the minus st dt. By the way, I should have put one more. Suppose an is non-negative, ax is equal to this, is equal to O of x. Let's put that in as an hypothesis, okay? Now, there are some remarks in Akshay's paper that this assumption really isn't necessary, and it can actually be deduced, but it clutters up the beauty of the proof, so shove it in. Because in most applications, we will have this information. So it's just a kind of a technical issue. So let's not worry about it. So let's just assume that we know it's O of x, and now from this meager information, we're actually deducing a more stronger theorem, like asymptotic formula. Okay? So now this has been set up. A of e to the t is O of e to the t, so this whole thing is bounded. So this is my f of t that I'm going to apply this lemma to. F of t is bounded, and it's locally integrable. Well, this is just a step function, locally integrable, okay? So this satisfies the conditions of this particular theorem. This converges now, we're saying suppose it admits an analytic continuation to this larger region, which is what this is now. Then immediately it says that I can plug in s equals 0 into the thing. I can plug in s equals 0 into this. Something's fishy. Yeah. Right? Here? Yeah. Pardon me?
When we replace s by s plus 1, so this should have x to the power s plus 2.
Oh yeah, thank you. Yeah, thank you. Yeah, this should be s plus 2. Thank you. Yeah, you're right. I goofed there. Yeah. Then I guess this is s plus 2 times t, right? Is that what you're saying? Yes. Okay. Thank you. All right. So now the lemma there tells me that I can plug in s equals 0 and say that I can plug in s equals 0 and say that this actually converges. And therefore I get the asymptotics. Does that make sense? So everything now hinges on, huh? I'm substituting x equals e to the t, dx equals e to the t dt, right? Oh, did I goof up here as well? Okay. So I have a of e to the t minus e to the t that, and then dx is equal to e to the power t dt. Yeah, you're right. And so this becomes 1 there? No. Oh, oh yeah, yeah. So it's just st. Yeah, okay, thank you. Yeah. Okay, so so I just need to prove this theorem. Hmm? So everybody happy with this so far? Hmm? All right. So I hope I can rub this off. Hmm? Everyone finished copying? Yeah? What? More wrong changes of variables? All right? I think it's okay now, right? Okay, the proof of this theorem is rather cute. So it relies on contour integration, so proof of lemma 2. So let's look at a circle of radius r. So fix r positive first. Large. And look at the circle in the complex plane. So we're in the complex plane. Now the point is that this function g of s has analytic continuation to real part s greater than or equal to 0. So what does that mean? It means that for every point on this vertical line, there's a little neighborhood, some neighborhood on which the function is analytic. Okay? So what I'll do is for each point, there's a neighborhood. So I get a continuum of points, continuum of neighborhoods, little balls, right? But it's a compact region here that I'm covering this compact region. So I can replace that with a finite number of balls. And therefore, the bottom line is that if the function is analytic for in this region, for a fixed r here, I could come, I'm not going to draw very small, but so that you can see it, I'm just going to put it here. So there is some delta to the left of the region, right, for which I can say everything is making sense on this part. So let's not worry about this part. In fact, I'm not allowed to go there. Okay? This is the axis. So this is the contour that I'm going to take. I'm going to first consider the contour. Now I'm hoping that some of you kids told me that you haven't had complex analysis. I really, really urge you to have a course in that. Sham's outlines in complex analysis is a good thing probably to study over the summer. And master at least the Cauchy residue theorem, contour integration, and so on and so forth. Because that's more or less what analytic number theory does, left and right. So it's a very important tool. Okay, so I'll start with this particular contour, and I will define another function, gt of s, which will be the integral from 0 to t, f of t e to the minus st dt. This thing, because it's a finite integral, converges for all values of s, so it's an entire function. It's an entire function because I've taken only a finite. What is t? T is also a parameter. T is also going to be fixed and large. We'll just take another parameter. Yeah? This is the kind of technique that will be used in analytic number theory. You start choosing parameters, and then playing with these parameters, and finally trying to get the thing going. So you have something like this, which is an entire function. Now, we will consider the integral. Now here's Newman's trick. Newman's trick was very cute. He introduces a kernel which I will speak a little bit more about this kernel maybe next time, but this is the kernel, what's called a kernel function in mathematics. So somehow you tack this on, and the idea now is that this function is entire. This function is analytic up to in this region that I've written. Because this C, by the way, is this whole thing along with this vertical line. Okay? That vertical line was determined because G had analytic continuation at every point, and because R is fixed, that determines a certain small line to the left for which it's analytic. Okay, so that's now by the Cauchy residue theorem. This is the sum of the residues, right? Well, where are the residues? Everything is analytic except this guy here, and the residue has to be at s equals 0, and at s equals 0, the residue is g of 0 minus gt of 0. Okay, so the limit as t goes to infinity, gt of 0 is equal to the integral 0 to infinity f of t e to the minus st, dt. That's what this is, right? And therefore, if I'm trying to prove that this converges and that this equals g of 0, then this is the quantity that I'd like to show is actually 0 as t goes to infinity. Okay, so we would like to study. We want to show limit t goes to infinity, g of 0 minus gt of 0 is 0. That's what we want to do. Okay. Now, the interesting thing about this particular kernel is it's got some nice properties. First property that it has is how does it behave on this particular circle? I guess this is what inspired Newman to calculate this thing. So observe that e to the st 1 over s plus s over r squared, this thing, is bounded by, well, let's write sigma to be real part of s. Then the absolute value is the product of the absolute values, right? So e to the sigma t. And let's also write s as r e to the I theta, so that here I'm going to get 1 over r e to the I theta plus r e to the I theta divided by r squared, absolute value. The one of these r's cancels,